Medical mixed reality. Mixed reality plays an important role in medicine by taking away the clinician's view from a separate 2D screen and back to the patient, by allowing the physician to visualize internal anatomy of the patient through the mixed reality device and project them directly onto the body of the patient. To effectively help with planning or with medical guidance, it is extremely important for the medical mixed reality applications to accurately align the virtual and the real content, for example, the medical images and the real patient. However, mixed reality alignment of virtual and real content is both challenging and also measurement of the alignment accuracy can be tricky. In 2D AR applications, like you can see here on the left, where each user sees the same screen, the alignment accuracy can actually be measured easily by just counting pixels between the virtual rendering and the real background on the 2D screen. In 3D, unfortunately, the things get a bit more complicated. So first, the alignment accuracy might differ between different users due to individual differences, such as the IPD or where the eyes are behind the display. And also the accuracy measurements are more complicated and usually require external systems. In this paper, or rather in this video now, we present an approach for landmark-based alignment, validation, and accuracy measurement of a 3D virtual overlay of medical MRI scans of the head on a real-world subject's head. As a first step, we take a 3D MRI measurement of the subject's head, including externally visible anatomical landmarks such as the nose and the ears. We then mark the position of these anatomical landmarks, which are used later to register the 3D rendering of the MRI scan to the real head. The position that we used for our experiments were specifically the nasion, the nose tip, left side of the left eye, and the left tragus. We furthermore place 6 virtual targets at arbitrary locations onto the subject's head. Here's now a video of the application view through the Magic Leap device. In white, you see the virtual controller with the cursor at the front, represented as blue dots. You can also see, not right now, but when the controller is back, the actual controller at the bottom, you see that they're not perfectly aligned. This doesn't matter though for applications, since for us it only matters where the user perceives these virtual blue dots. The user then places these virtual blue dots, aligns them directly with these anatomical landmarks of the real patients to place fiducials. And it's extremely important that the user places these anatomical landmarks exactly where he perceives the real anatomical locations. Once our fiducials are placed, the virtual head is registered to the real head. As you can see now, the virtual rendering is shown on top of the real head. You also see now here in white the 4 virtual fiducials that the user placed manually, as well as you see 4 more dots. These are the 4 landmark locations that were already present in a 3D rendering. By measuring the distances between these, we can now measure the fiducial registration error, which is also shown here at the top, which gives us a first estimate of how accurate our placement was. In green, at the top of the head, we furthermore see the virtual targets on top of the subject's head. The user now takes MRI visible capsules, these are little vitamin capsules, and places them at exactly the locations where he perceives these virtual targets. And one very important thing to note now about this video. This video was taken with the Magic Leap mixed reality capture, where the alignment between the virtual content and the real content is slightly off. So it doesn't exactly represent what the user sees in the Magic Leap headset. That's also why you see here right now the alignments of these virtual and the real fiducials, or here, for example, of the ear, seem to be quite off. The user perceived this more accurately inside the actual headset. Now we see all these markers are placed at the virtual fiducials. The user could now go around the head, look from different angles, adjust the position of the capsules until the Magic Leap user is really happy with the alignment of these capsules. You can also change the rendering if it helps you with the alignment procedure. So you have the freedom to do that as well. Now in reality, this if you don't do it through the mixed reality capture, but if you just place them without taking video, the procedure is actually much faster. So here we see view from outside, where you unfortunately do not see the virtual content, but you place virtual fiducial at the nasien, nose tip, left eye, and left ear. Once these virtual fiducial are placed, you adjust the head, and now already the users, after you saw it was it 10 seconds, 20 seconds, the user already sees the virtual rendering accurately aligned, and then can start placing these MR visible capsules. After all capsules are placed, we then took the volunteer to an MRI scanner in the same building, and we made sure that the volunteer did not move the cap with the attached MRI visible capsules, so that this was really like no movement, no capsule moved around. And then we directly took a second MRI scan. Directly after placing these capsules, we took a second MRI scan, which included, as you can see here now, the position of these virtual capsules on the subject's head. We then registered the second MRI scan to the initial MRI scan. And you can see here, since the capsules are slightly off because of hair of the subject and everything, we then projected both these capsules and original targets back to the surface of the subject's head. And this allowed us now to measure the target registration error by measuring this distance between the capsule projected on the head surface and the targeted projected on the head surface, which represents the alignment accuracy for our experiments. Before COVID arrived at Stanford, we were able to measure 7 volunteers. And here you see the different experiments. They are also shown in detail in the paper, of course. And we measured a mean target registration error of 4.7 plus minus 26 millimeter over all these 7 volunteers. We also have more details on the measured results, including potential error sources such as swim or drift mentioned in the paper. I won't discuss that too much now in the video. It's not so interesting for the video. I rather want to talk about applications that we are using and that we are planning to use this technique with. So 4.7 millimeters is of course not good enough if you want to start neurosurgery and start cutting open the brain. It is, however, quite good for our intended application, and that is for guiding non-invasive brain stimulation treatment. So here I show an example where we are again performing the same registration procedure. We combine this registration procedure with some tracking. So after the head is aligned to the patient's head, we now track the patient's head position with a marker that is attached to the patient's head surface. So first, again, you place your virtual fiducials at these different, this time see we have different underterminal landmarks for this case. Then you register the head. Once it's registered, we are tracking the head using this marker. You see when the patient moves their head, there's some slight delay, but the pose is kept. And now, I'll pause for a second, now we have this electromagnetic coil. So this medical application that we are trying to guide is so-called transcranial magnetic stimulation, where you have an electromagnetic coil that you place close to the head, and the electromagnetic field then induces currents in the subject's head. So it allows you to stimulate the brain from the outside without actually opening the head. And the focal point of this TMS coil that we're using here is about the size of a quarter. So 5 millimeter target accuracy, or even less than 5 millimeter target accuracy that we have achieved, is actually really good for guiding this technique. So let's keep the video rolling again. Now you see if you place one example of what you could do. If once you place the coil close to the subject's brain, we could see, for example, functional networks that would be targeted for a certain coil position. Then finally, I would like to thank you for listening. Please write me, of course. Here you see my email address if you have any questions. And also would thank to the whole Immerse lab at Stanford that helped with the experiments, with taking the videos, that working on a variety of different applications of mixed reality in medicine. Thank you very much.